It's a great pleasure that I get to introduce Pete Laz, who's actually over here just for a couple of days en route. He's on sabbatical at the moment. Spent a couple of weeks over in Adelaide with another colleague of ours, Mark Taylor. And Mark and Pete share an interest in probabilistic modeling. So they don't believe in just one number, it has to be lots of numbers. Hopefully where they can calculate means and standard deviations and apply those to our knowledge of the musculoskeletal system, and in this case, in orthopedic biomechanics. So Pete is a professor at the University of Denver, and I actually was fortunate enough to be involved with one of Pete's ex-students, Symonds St, who's spent a little bit of time here at the Bioengineering Institute. So Symonds did his PhD with Pete and Paul Rollcutter at Denver, and then moved on to, of course, bigger and better things. No offence to Denver. But it's great that you're here and could be with us and could just swing by for a quick Tuesday seminar and talk to us all about some of the new work that you're doing, particularly as we'll see in the Centre of Orthopaedic Biomechanics at Denver. Is a great group of researchers there, and they have some really neat tools which they're now applying with anger to understand orthopedic problems. So again, thanks for being here. And thanks for giving us this talk, and we look forward to listen to what you have to say with the research.
Yeah, super. Thanks so much. It's been already a nice day. I've had some great conversations with folks, and I think we wind up thinking about some of the same problems. And so much of what we do in biomechanics is driven over here on the left side, right? We make models of one person or a small group of people. When we do experiments, right, we're collecting data on small handfuls, small groups. And ultimately where we want to go, as far as designing implants, designing treatments, we really want to be pushing towards larger populations, having our work be more meaningful. And so, as Tor was saying, a little bit about who we are as Center for Orthopaedic Biomechanics. So it started Paul Rollcutter and I some 15 years ago. Paul does more dynamic musculoskeletal finite element models. I do more probabilistic and shape models. And we just started working together and partnered up. And we have since grown. The slide used to be a lot sparser, but we've been filling in some of the pieces around in vivo human dynamics, and then also have added now cadaveric and retrieval lab. And so we've got a good group. A little bit about Denver. We're located centrally, Rocky Mountains. I think one of the things that's nice about it, and is probably comparable to here, is that you have the offerings of a city, but then you can also get out and do things outside. So this is what we look like now. And I'm sorry about the politics. It's really, it's more of a disc. Yeah, I'm sorry. That's really all we can say. So we recently have gotten a naming gift for our school, and with that has come this new building. We were looking at architects' renderings for quite a while, and now we're fully moved in, and that's the picture of the building just before I left. And so what's in the building? Well, we've got some of the traditional motion capture types of equipment, so Vicon, ground reaction forces, very similar to what you guys do here. We have been fortunate with NSF support. We're able to obtain a stereoradiography system. Some folks call it biplane radiography, but essentially can now track motions of joints in particular. You can see we have configurable gantries, so you can change the heights of these detectors, configure them so that you can image the joint that you're interested in, whether that's ankle, knee, foot, hip, shoulder. We've even done a little bit of spine. And so the idea is that you take some video and then you do tracking in 3D with your geometry and can accurately, to sub-millimeter, sub-degree accuracy, to describe those motions. And so this is pretty neat. I have to show a couple of animations. And so you can see it's quite nice, the images. And so this is, we feel, an important piece to the puzzle. So when you get the whole body motion, that's great. But a lot of our questions are around joint mechanics. And this tool has some pretty nice accuracy for it. You can see that we're collecting, you can see the Vicon markers, and you can see the EMG is also taken as part of the data collection. So trying to expand what we're able to collect as a data source. So this opens up all kinds of new lines of research for us. We think this is going to be a big market. All right, maybe not. The kids' toy industry doesn't quite have the research opportunities we were after, but we are interested in trying to look at more challenging activities. So instead of just looking at lunge, actually looking at sort of a pivot, internal, external pivots. So that's a little bit on the in vivo side. We do, like you guys do, lots of subject-specific models. So starting with imaging, developing a subject's representation of their anatomy, and use a variety of representations from ligaments as like individual point-to-point springs, sometimes as fiber-reinforced membranes, sometimes as full 3D structures, and are also doing some work where we map material properties for bone to be able to look at some fracture types of problems. And then with the fluoro data, we can drive some of those models. It's challenging because even with that level of accuracy, there are still some challenges with contact mechanics, as I've talked with folks today. But we feel it's a nice platform for being able to look at contact mechanics. And then Kevin Shelburne and Paul Rollcutter on our side have been doing some musculoskeletal modeling, but with compatibility within an FE framework. And so this is actually an FE. There's an open sim counterpart to this model. And we can see it's looking at the weight acceptance portion of gait. We've got one knee implanted, one knee natural, and really trying to then look at some of what's the joint contact that's associated with that. So trying to add more detailed joint representations. And then similar to some of the things you guys are thinking about is this idea of three-dimensional muscles. And so in this work, really interested in sort of this thigh-calf contact and what's that doing to the joint mechanics there. And so those are a 3D representation of the muscles. And then some of the work that I've been doing in collaboration with folks in Bologna is, again, very specimen-specific. And we find that you need to have these specimen-specific models to have the fidelity to really get at the mechanics of what's going on. And so this is an XFEM model trying to look at fracture over here on the right. Here's the experiment. And so you can see we're able to predict pretty good agreement as far as the onset, and then also some of the fracture patterns. And so then the most recent piece that's, as we've moved into the new facility, is really being able to do cadaveric tissue for us for the first time. We've regularly used experiments, but I've always had to partner. We've partnered with folks in Washington or Kansas or some other universities to run the cadaveric experiments. And so we're excited to have that now in-house. And we have sort of a 6 degree of freedom simulator, and then also some implant retrieval to do a little bit of close the loop. So that's a little bit of about us. I think that's helpful just to put some context in it. So we really try to use all these various tools to try to have an impact. And most of our work is really themed around joint replacement. And as folks are familiar here, osteoarthritis is a big deal. It affects lots of people. We're coming up close to 1 million total joints per year. And that number is expected to spike, right? It'll be 3 times larger by 2030, right? So this is a growing problem. And in general, joint replacement is successful, right? Patients experience the reduction in pain, good survivorship, reasonable satisfaction. But we can say patients are surviving, but the questions are they thriving? And so we feel that there are some opportunities here to do better. And so when you look at the numbers there's 20 to 30% of patients who experience significant functional limitations, pain, or require additional surgeries. Up to 20% are unsatisfied. And you still do have, while survivorship is good, there is the flip side of that says that there are still revisions that are happening. And so when you think about the growing populations and these percentages, there are I think a large cohort of folks that we can still have an impact on. When you look at what are the causes of revisions, what are causes of the challenges, a lot of it is related to loosening and wear, and factors in that are obesity, challenging activities, and underlyingly, we think a lot of this comes from factors of the patient. There's some specific characterizations of patients that can be challenging. There's the implant design piece, and the implants are pretty good, But there's also a big alignment component to that. So if the component goes in malaligned, it alters the loading condition. You couple that with a patient factor. And so there's a lot of interaction here between patient, the implant design and alignment, and then the loading. And all of that comes together to influence then the outcome. And so a lot of what my work is thinking about sources of variability, trying to understand these various populations, and then developing some tools that we can use to improve things. And so we think about intersubject variability, right? Wide range of people, even on things like mechanical properties. When you do measurements, coefficient of variation, so standard deviation to the mean, it's 30%, right? Lots of variation is present. You add in a surgical variability component. These are standard deviations of multiple degrees, multiple millimeters in terms of alignment, and that would be from a neutral target. And so that's the standard deviation. And when you think about the population as plus or minus 2 standard deviations, pushing plus or minus 3 standard deviations, you get out to some pretty large numbers.
Sorry, can I ask a question?
Yeah, sure.
Is there a clinical validated tool to get objective measures around the outcome and the quality of life and etc. for these post-surgical knee replacement patients?
So a lot of folks will use surveys. So there are a number of clinical scores that people are, and so it's a combination of a questionnaire to the patient, and then some measures, some basic range of motion types of numbers go in typically to those. That would go to sort of become an outcome score. But what isn't currently happening, which we advocate for, is actually going into a gait lab or a human dynamics lab or motion capture lab and really trying to understand how they're actually performing. And so that's sort of our approach, is to actually take those measurements. And we have partners at University of Colorado who do rehabilitation and are then tracking patients after these. So oftentimes we'll do a pre-assessment and then track them after. And so we're actually starting to capture some of that data and put the quantitative numbers behind it. Yep. Okay. So intersubject, surgical, and then loading variability. So loading variability, we all move differently, right? In the ortho load, they've now been taking measurements of what the loading conditions are. And when you look across hip patients performing the same activity, you see that there's quite 100% difference in the range of their peak load, and you have the range of body weight. And so essentially really very different loading, potentially, that an implant or a joint may see. And so one of the things that we regularly are thinking about in this is that you have all these sources of variability. Some of them can be controlled, right? We have potential to influence through instrumentation or design the alignment of an implant, right? We can potentially influence this one. But a patient factor of how they move, right, or what their underlying anatomy is, we have to accommodate, right? And we have to design implants that can be robust to accommodate the variabilities that are present. And so a lot of what we do, or a lot of what is typically done, is you have your inputs, they go into a model or an experiment, and you have an output. And what I advocate and what our lab has been really integrating into everything we do is to say that these are actually distributions as inputs. We put them into some sort of probabilistic wrapper that can go around essentially any model and then predict distributions of outputs. The reason we like this approach is that you get more information. You don't just get a mean line. You can get some sense for upper and lower bounds, and you get measures of interactions between your input parameters, and you learn which ones are most important, right? And oftentimes that can be helpful to identifying patients or identifying alignments that could be challenging. So we use a variety of different tools, Monte Carlo simulation, which I'm sure folks are familiar with. We use some efficient probabilistic methods, and we use principal component analysis quite a lot. The challenges in this are really understanding these inputs, and in joint mechanics, a lot of what we do is multifactorial. As in, you've got kinematics, you have contact mechanics, fixation, wear. There's a whole list, load transfer. There's a whole list of things that you're trying to look at as outputs. And really there is going to be some trade-offs that need to be made between them. So it's definitely challenging. What I thought I would do is present a little bit on some of the shape modeling work that we've been doing, and then a few different applications. And depending on how we run with time and questions and things, I've got a number of different bailout points, right? So if this is interesting, I'll keep going through it. And when you get to the okay, that's enough, then give me a signal. So as far as shape modeling, we've been working with MRI data sets to try to then build a shape model of the knee. Lots of folks have been doing shape models. Most have been around whole bones, right? I think the unique part that we offer is that we've been looking at this from a joint perspective, and we're a little bit limited because oftentimes our scans are just near the joint region, but we have been capturing the femur, tibia, patella, the associated cartilage, and then also have been looking at some of the attachment sites for those. Our populations are from both cadaveric testing and from the osteoarthritis initiative. That's an NIH-supported study. These are all healthy, so even the OAI subjects were from that initial introductory scans. And so essentially we built then these shape models. And so process is segmentation, alignment, and so we represent the bones as tri-surfaces. You could easily make them into tets. For us, the cartilage surfaces are all hexes, and our motivation is really to have these be linked to finite element analysis to be able to run contact simulations with them. And so all of this operates on sort of an FE type of mesh that allows us to then run those analyses. And we can represent each one of these subjects as a vector, and the vector is the nodal coordinates, and then some 4x4 transformations that describe where a structure is relative to the other structure. And so once we have that data set, we perform principal component analysis. And so PCA is all about a dimensionality reduction. And so the very simple example is over here. If you have this cloud of data, it shows in 2 dimensions. And so you could represent this where you mostly are looking at the 1 dimension of the signal. And so essentially, when you do the eigenanalysis on this, it determines your principal components. So you could separate signal and noise. For us, we look for the early modes, which describe the variation that's present in the data. And then you get a ranking through your eigenvalues of how much of variation is explained in each one of those modes. And then we'll oftentimes typically represent individual subjects in that PC space. And we think that that's interesting for looking at trends among ethnicity or gender, things like that. And so this is this is one of our first early shape models, was looking at cartilage of the joint. And you can see this is cycling through the modes. And so so the first mode tends to be a scaling mode. Here it is, scaling mode. And then we see then some shape changes in mode 2, and then a different set of shape changes in mode 3. So that was the first one we did. This is now the one that includes the bone and cartilage and the attachment sites. And so mode 1 is largely a scaling mode, right? It turns out that it's actually non-uniform, and I can get into that in a little bit more detail. In mode 2, we see some differences in the placement of the patella, so alta baja of the patella. We also see lots of differences in the conformity of the patellofemoral joint. And then in mode 3, it's difficult to see in these pictures. I'll show in a later slide. There's coverage of the cartilage as well as some orientation of the patella. And so we're able to describe then some of the variation that we see in the shape model. And again, it includes the ligament and muscle attachment. So we have tried to include the quadriceps mechanism so that we can actually run these in FE models. Have been doing a lot of shape models. Tor said when you have a hammer, everything looks like a nail, right? And so we've been doing lots of shape models. So we have the knee. We've been doing work in the humerus, and so the size of the populations are here. We've been doing scapula, where we're including the material maps for those. We've been doing foot, and we've been doing some lumbar spine work. And in lumbar spine, it's interesting, we're able to take this and then do some templating where we apply flexion extension in the model and essentially try to identify candidates who total disc replacement will work better than fusion. And so, yeah, excited for that as sort of a pre-surgical tool. Yeah, question?
Do you have to worry about point-to-point correspondence with these sorts of shape models? And how do you deal with that?
So we have done that. That was sort of back.
Just with the template.
So we align the template, and that's where we established that that nodal. We definitely established nodal correspondence. Yeah.
So then, when you walk that template to the actual geometry, you're just hoping that you've maintained that kind of point-to-point correspondence from subject to subject. Is that the idea?
Yes. Yep. And I think we're pretty confident in that. And I'd be happy to explore that in a little bit more detail with what we're doing. Yeah. So we previously used a lot of iterative closest point to do that, and now have been doing coherent point drift is the tool that we've been using for that. And there's a publication in a MATLAB script that we've been using. Works quite nicely. And so I think we feel pretty good about that, and have done some proofing of anatomical landmarks to make sure that those points, when we're using them that way for measurements, wind up working out. All right, so we've established shape model. There's the saying form follows function. I don't know if folks know Louis Sullivan. Folks have probably heard of Frank Lloyd Wright. He's an American architect known for sort of falling water and has his own style. Louis Sullivan was Frank Lloyd Wright's mentor and sort of, for us, coined this phrase. I don't know if it's, that's where we attribute it to. Anyway, we're thinking about form as in the shape of the knee, and function is how the knee moves. And so a unique part of our data set was that we had cadaveric specimens who we applied the same loading conditions to in the Kansas knee simulator over here. So we had their shape, and we have their motions, tibiofemoral and patellofemoral, for in this case, a squat cycle. We have other activities as well. And so essentially, with principal component analysis, you create your data array, right? And you can perform your eigenanalysis on it. And so in this, we took the form data and the function data and put them into one large principal component analysis. And then when we look at the modes, what does it tell us? Well, it tells us things about how does the shape change at the same time that the kinematics are changing. And so we think this is pretty neat. And so what we noted here was we saw that there were these scaling differences in mode 1. It turns out when we look at the condylar geometry, people would call this sort of the J curve. You can look at the geometry. On the medial side, we see pretty even scaling. On the lateral side, we see some differences here. And you see the radius of curvature is changing. And so what we do to visualize this change in the mode is we perturb it at plus or minus 1.5 standard deviation. So you have the plus mode and the minus mode. And what we noticed was that it was changing pretty dramatically in some of the kinematics. And these are the kinematics folks care about in joint replacement are AP and IE. So how much rotation you have, how much movement in AP. A lot of times folks will look at, in fluoro circles, we'll talk about the lowest contact point or where contact would occur on the condyle. And so when you have this complex motion of internal external rotation and anterior post AP translation at the same time, sometimes difficult to visualize. And so folks will put the contact point, right, proposed contact point on these. And so you can see that and it's got a little bit cut off. So red is 0, green is 30, 60, and 90, right? So as you flex, your contact moves posteriorly. And so pretty interesting that we can use the shape of the knee, right, is driving a lot of the motions. And we can delve deeper into this and look at then more patellofemoral type of articulation. And so it turns out that if you're alta or baja, so the height of your patella, right, thinking about alta and baja, that wound up influencing a number of different kinematics. So oftentimes flexion, but also we saw that it influenced the AP translation, which is essentially the moment arm, right, at which the patella is acting, is going to be influenced there. And then we further saw in mode 3 sort of changes in green, right, as mode 3 was dominating where the positioning of the patella was responsible for some of the changes that we saw in terms of internal-external rotation. So I don't want to get too caught up in the details of this. We've published on it in JOR. But I think what's interesting here is this principal component analysis tool. And so with the shape model, we've done a couple different applications. And so one of them is thinking about stereoradiography. And many studies have looked at tibiofemoral kinematics, right? For an implanted joint, that's quite easy to see, right? The implants show up. You don't even need to do additional scanning. You just use the CAD from the model and you track them. On the patella, there hasn't been very much work done because the patella is a polyethylene button, right? And so you can't actually see it. And what you're left with is the resected bone surface. And so in order to actually look at patellofemoral kinematics, you have to make some guesses about that plane, right, and the resected bone, or you have to work with a beaded implant, which is a specialized implant which requires FDA approval and things for us, so that's challenging. And so our idea here, and this is building on some of the current work in this area, is folks are using shape models to be able to track natural knees without having to do an initial scan, right? So typically you would have your geometry that you would then position in a way that you would match your stereoradiography images. And so we were interested in seeing, could we do this in the patella, specifically around the implanted patella, and we'd have to come up with a way to deal with the resected bone, as well as to pose the patient in a way that you could really see that patella and have it be really visible. So again, shape model, looking only at the patellar bone. We've got these 50, and we see clearly the different modes, a scaling mode, an aspect ratio mode, and then a facet ratio type of mode. And so we wanted this to be very real, but we also wanted to do this in a computational platform and figure it out before we started trying to collect this data on patients. And so we did some initial positioning just to get a sense for things. And so if we have the subject prone, and we do this first, we can actually do this within the workflow of our protocols. And essentially we're trying to capture sort of a merchant view is the image in A, and then you get the sagittal view. And then we thought if we could rotate that patient around, we could then look at some of the other views and built this into a virtual platform. So the way that this works is we would do a leave one out type of evaluation. We would have a subject's patella. We build the shape model with all the other patella. We go through and we auto implant. So develop the resection profile, place the patella. So this is virtual implantation. So we now have a resected patella. We position it and make a projection for what we think A and B are. And then we used an optimization algorithm where we used the shape from the shape model, and we used oppose XYZ rotations translations and tried to predict that subject's patella. And so what we're doing is when we start, we place the average size bone, and we're obviously not doing very well. When we go through the optimization, and this is considering all 5 of these positions, we're able to match all 5 of them pretty well. And as we considered more positions, so when we did one position, you can see that we did pretty well on the 0 and 90, but we didn't do well along the 45s. As you add more of the positions in place, you fill in the accuracy. And so, not surprising, the 2D errors of how we match the profiles increased as we added those more positions. Because we're adding more information, it's more challenging to try to fit. But the 3D error of how our geometry that we're predicting compared to the actual subject that was left out improves each time. And we're down to an RMS error of 0.45 millimeters, which we feel is as good as what you could get out of segmentation. And so we feel really are happy with this approach. So this virtual platform was used to develop the protocol. No exposure to patients. Accuracy is quite good. And so we've gone ahead and have now started taking this data. And so this is nice because we'll have combined tibiofemoral and patellofemoral without additional scan or inconvenience to the patients. And so it really is sort of a value add to us in addition to the tibiofemoral. All right, how are folks doing? I got a couple more of these sort of, if we're doing all right. Yeah? All kinds of things you can do with shape models. Obviously, we're big fans of cartilage, right? I think most of us are rooting for cartilage to win over joint replacement. Cartilage is great, protects bones, facilitates smooth motion, reduces pain. And folks are looking at cartilage for disease progression. We regularly think about it for computational models, contact mechanics. And then even in joint replacement design and placement, they're trying to reproduce natural mechanics. To get to those final percent to improve outcomes really means making the joints more natural, right? And so if you want to add cartilage to your model, oftentimes that requires manual segmentation, right? So going through slice by slice of an MRI scan. There are some cases where you have data and your data is in CT, right? Your subject data is CT, and so you don't actually have cartilage information at all. You can't see it, right, over on the far side. And so we said, we have this shape model where we have bones and cartilage. Can we use this to, if you have a bone, can you predict cartilage? It's a very simple question. And it's also really hard, right? So shape model, here we can see we have the scaling mode, we have the shape conformity mode, and in mode 3, I want to highlight this difference of coverage variability. So how far the cartilage wraps around the condyle, right? And you can see it also here in the patella. That's what is captured in this third mode. And so the way that we do this is, again, a leave one out evaluation. We leave one subject out. We build our PCA and then use the bone-only representation to score that subject as a series of PC scores, right? And then based on those PC scores, we then use that combined model to then populate the cartilage that would be associated with the left out subject. And then we do the comparison between the predicted and as segmented. Okay, so here's where we are. I did mention this is hard, right? And so we see pretty good sort of trends, right? But it's clear that we're not quite there. So if we look at 3D geometric errors, we're able to represent the bone itself pretty well, right? 0.57, 0.6. That's on the order of what you would expect from sort of segmentation types of errors. So we're capturing the bone pretty well. On the cartilage, our errors here are above 1. On the tibia is closer to 2 millimeters, right? When we look at thickness, our errors are around about a half a millimeter. And so you can see that there are some differences in terms of where some of the peaks are, right? Where you have thicker cartilage. And so this was our first order crack at this. And so what we wound up learning here is that in these predictions, we can look at relationships between our combined bone cartilage model, and we can look at relationships to bone only and cartilage only. And what we see is that when we look at the relationship between bone and bone cartilage, this is a correlation between each one of the modes for bone, for individual model, and then for the combined model. And we see pretty strong agreements above 0.9 for the first 2 modes. Mode 3, we fall off. On cartilage, we're well represented. What that means is that when you think about that cartilage coverage mode, you don't have data from the bone alone to be able to describe that behavior. So that's a challenge. I wish there was a happy ending, but this is current work in progress, and we're still working through it. And so, but we think that that is the challenge. And so when it comes to doing subject-specific models, the accuracy that we're seeing here may be sufficient. We have ideas of, if you had a total knee replacement patient, oftentimes folks are, when they're doing the pre-surgical plan, they'll oftentimes put a constant thickness layer of cartilage on it to try to understand the joint spacing. We have some ideas around also looking at some of the joint spacing from MR and maybe using that to help scale things as an additional piece of information. But we think it's interesting to think about this type of approach to go back to a pre-OA state. And then these days, folks are thinking about additively manufacturing implants, right? Personalized implants, personalized instrumentation, that these kinds of tools could be helpful in terms of trying to represent that cartilage. Okay. So one of the areas that we're interested, go ahead, question.
You mentioned that from the bone alone, we cannot project the actual cartilage, right?
We can predict it this well.
Yeah. I'm wondering, can we have some reference point from the segmented MRI just to have more accurate cartilage modeling, cartilage prediction?
Mm-hmm.
I don't know, have you ever tried to get some reference point instead of the whole segmentation, just using particular segments to have accurate prediction? Is this possible?
It's interesting. So I think what we're seeing is we don't have enough information here, and this comes back to this, right? So we can do well on we can scale cartilage well, we can capture the shape conformity well, but we had challenges with this coverage piece. And so if your modality is CT, we were trying to do this blind, right? So if you had CT only, you wouldn't have the information. And so I think that's the challenge. If you had MR or you had additional information, then I think you could do better. And so I think this is a little bit of thinking about the specific application and even thinking about some of these joint spacings, right? So if you had some information about joint spacing, maybe we could do even a little bit better. So anyway, that's sort of where we're at. So some of the direction that we're going is towards population-based evaluations. So we have the shape model. We can generate instances from it, and we use a number of different sampling strategies, from just basic Monte Carlo of randomly sampling, or maybe doing a more targeted Latin hypercube where you select a smaller subset, but spanning the population. We then do some automated sizing and alignment. So we do a virtual implantation, and then essentially run these models, and in this case doing a bit of a deep flexion squat type of cycle, and then collect a bunch of that data. And so we think that kind of approach is pretty nice. And so you can know information about where you sample from the population. So we show a number of data sets here. One is from Mafuz, where there's 1,000 knees from all different ethnicities, both genders obviously, and that's sort of the blue line. Our training set is this black line, or the black points. When we did our Monte Carlo sampling, we had the green, and then you have the Latin hypercube, which are just 12 subjects, but distributed among the population. And this is one measure, but you could do this obviously for more measures. So you get a sense for where you are in the population. We think it's interesting to also look at implant sizing lines. And so in the patella, there were 4 different patella implant sizes. And so we can look at some of the geometry there for that population and see which implant they would typically get that would fit them well. And then if we populated this, there's 100 points there, but we could populate that even denser and really start to refine sizing lines so that they best capture the population. And then try to then make some links to motion, right? So we show for a subject along the top what happens kinematically. And so we're not driving, we're driving that implant, that model with, it's a load control model. And so then we can look at then what would the resulting kinematics be, and they're going to be influenced by the implant and where that implant is placed. And so we've done some looking at, and this is quite early, but more of a concept, is thinking about some of these implant sizes and how the kinematics, how the motions are linked to that, right? So it turns out the kinematics, how much AP range of motion you have and how much patellofemoral range of motion you have, ML, this is PF, how much of that changes as you change your implant size. And then some of the other things we're thinking about is, so this is on the implant sizing, but then we can also think about patient factors like alta baja and how much flexion extension or some other degrees of freedom, sort of ML over here, how much that changes with some patient factors. And so we think this is all pretty interesting as a framework for trying to really dial in implant design, implant sizing. All right, so I think I have one more left, and you guys seem like you're still here and with me, so that's good.
Can I ask a question about your last study?
Yeah.
So you, if I got you right, you were looking at a single bone to try and predict cartilage, and you mentioned if you had joint, maybe bone separation, I guess, or joint separation, you might be able to do better. Why not do the shape analysis on the joint as opposed to just a single bone? Or did I miss that?
So we did it as a leave one out. So in each evaluation, we would take one bone and then run that analysis. And then we cycled through which bone was left out. So we did it for all 50 of them. And what I reported was I think it was an average absolute geometric error. So we did leave each one of the bones out and tried to predict it. So we did it for all 50 of the subjects. I'm sorry that wasn't clear.
I understand that, but I thought you were able to add, you didn't have enough information to predict the cartilage shape, I guess. And you said if you're able to add, I thought you said if you're able to add the bone separation, or I don't know what term you used.
Yeah, so I think so if you're thinking about CT, the cartilage doesn't show up at all.
The two bones do. So
the two bones do.
Bones in the shape analysis.
Yeah, so that's one thing that we're thinking about trying to include, but we have not done that yet. But it'd be interesting for sure. Yep, and I think worth trying. So, all right, so this is the last one. And so this is thinking about in hips. For total hip replacement patients. It turns out implant alignment is regularly associated with complications. And we're trying to really understand, so it turns out that the alignment of the hip is going to influence the loading. And so interested in having a tool that can help to assess what are the joint contact forces and muscle forces in light of that potential malalignment. And so the idea here is to perturb the positioning of the cup and the stem, head center essentially, and then look at what impact that has. And so we've done some work with Probabilistic OpenSim, and this is in collaboration with Kevin Shelburne, and Casey Myers is the postdoc who's done this work. But essentially I've come up with a plugin. I think it's called the Probabilistic plugin, as in like plug-in in the socket. And so essentially allows you to make some of your OpenSim input parameters, instead of being an average quantity or a single quantity, represent them by distributions. And so in this initial pilot where we introduced the tool, we made marker data a distribution, carried that through. And so this workflow, I think, for OpenSim folks should look really familiar, right? You come through inverse kinematics, get joint angles. We carried the uncertainty from joint angles forward, but also added in body segment parameters, right? And then that went into inverse dynamics and gives you your joint moments. And so then your joint moments are now a distribution of inputs, and then we included in distributions of muscle and tendon properties to get distributions of muscle forces. And so in that original publication, it includes then looking at this propagation of uncertainty through that framework. And so you can see you get bounds, 5 and 95% bounds for your kinematics, carried forward 5 and 95% bounds for your moments, 5 and 95% bounds for your muscle forces. And so we kind of like this approach to be able to think about sort of a range of quantities, right? Because there are some uncertainties that are present in a lot of those inputs, and a lot of them are based on average relationships. And so essentially we've applied in this study that probabilistic plug-in to look at perturbations to the joint center, the hip joint center. And so considered variability in, and this doesn't look focused to me, but in 3 translations, 2 rotations. And so when we made perturbations on the femoral side, we moved the head center relative to the bone and kept the femoral attachment sites for all of the muscles spanning the hip. They stayed in the same place. When we moved the cup, in which case if we moved the cup, we also moved the bone went along for the ride, right? So we're capturing both of those scenarios there. We ran this in open sim models that were subject specific and tuned, scaled and tuned, and I know that that has a variety of different meanings. We think we've done that well. We had some isometric strength data and tried to tune the properties and calibrate the model to give a good result. And we looked at 3 tasks, so gait, sit to stand, step down. I think there's 5 patients in this cohort. And what we were after is confidence bounds on the joint contact forces, the muscle forces. And this really doesn't come out very well, but there's actually a whole cloud of data points that would be there that we would look at sensitivity, so as in which parameters are important. So the key findings as takeaways from this was we first did a comparison to some of the orthoload data. The orthoload is in sort of the white, and then our 1 to 99% bounds for this representative subject is shown there, so we feel pretty good about that agreement. We found that stem anteversion, so for the stem, anteversion was most important, and for the cup, the medial lateral positioning were most important. And so what we're showing is in the dark blue is the stem, light blue is the cup, and so anteversion is here and is slightly off the screen there. We have sensitivities for joint contact force here, sensitivity for muscle forces there. It's sort of a surrogate. We've consolidated quite a bit of data to get in to make it a quick, clean story here. And then ultimately we wound up showing that the SI position, so superior and inferior positioning of the cup, had the greatest impact on the direction of that joint contact force vector. And specifically, as we're shown here, as you move inferior, that joint contact force vector is moving up towards the equator. And so we feel like there's some implications there for potential for dislocation. And so, all right, I think we've made it to the end. And so we know that outcomes are influenced by patient factors, implant and alignment, and loading. And in our opinion, right, my opinion, understanding this variability and its impact is really important. And so have tried to show through shape modeling some of these probabilistic methods, the ability to describe anatomy, which can be used to improve implant sizing and fit, the ability to identify patient and alignment factors, potentially interactions between what's happening, what the patient's anatomy is, where the implant should go, and show the impact on joint mechanics. Showed some links to stereoradiography. In the cartilage, tried to show making a sparse data prediction. And I think a lot of this is really, in my opinion, about creating some of the computational infrastructure to enable some of these population-based types of analyses. But I think the goal is to improve robustness of implants, instrumentation, and surgical approach. So I have to say I've been fortunate in my position to work with some really good people, some really good students. My advisor was Ben Hilberry. He was faculty at Purdue for many years and passed away after a fight with Alzheimer's for a number of years. And it's interesting because he wasn't the most published professor. He didn't have the biggest grants, didn't bring in the most money. He wasn't the best teacher. But the one thing that he did really well was work with graduate students and help graduate students grow and connect people. And that really stood out for me. At his services for the funeral, his family said he was about family, he was about sailing, and he was about grad students. And so when he retired, he had 100 graduate students in his career, and some 60 to 70 of us showed up and came back and saw him off. And that was pretty special. And a lot of that is sort of when I look around at my professional network, many of them have strings to bend, and for that I'm really grateful. And it's one of the things that I try to instill in my students, and I think it's an important message, is that it's good to have, it's good at the end of the day, we can do some good science and do some good research, but I think those relationships with people wind up being really important and really impactful. And so I've been fortunate to work with folks from a number of different places and really want to acknowledge that interaction. And then, yeah, we'll say thank you to the research sponsors. So, yeah.
Great, we still have some time for questions.
So when you do variation of input parameters or distribution of input parameters for a modeling approach, you sort of have a choice of, well, control these variables and then we'll vary one variable one at a time, right, and look at sensitivities and that kind of thing. Or you can sort of vary all of the variables and run simulations on all of the variations. So the second one, you obviously have a huge number of simulations, and sometimes that becomes unfeasible. But with the former, you have the issue of nonlinearity, of constitutive properties of tissue and all geometrical properties. So I guess I'm just wondering, which approach do you take, and sort of what's your stance on nonlinearity and how these things, what's the meaningfulness of sensitivity analysis?
Yep. So I think you've done a nice job framing the question, right? And so I believe you want to capture interaction effects in your models. So I believe in mixing it all up, right? And so the challenge of that is if you do Monte Carlo simulation, which is taking each one of your input parameters, randomly picking it according to its distribution. So it's not really random, but you're randomly selecting it from the data you have on mean and standard deviation. And if you oftentimes that can be intractable as a problem, right? You have too many analyses that would take too long to run. And so in my lab, we're a huge fan of some of the efficient methods. And so there are some approaches that allow you to, depending on what your output is, right, and what you're interested in overall in the study, but there are some efficient ways that you can do that sampling to explore the part of the area that you're most interested in. And so a couple of them are like advanced mean value, right, or form, first order reliability methods, but they only give you a part of your solution. So there's always trade-offs. There's no free lunch, right? Although, yeah, I don't, yeah. And so I think, yeah, if you have specific, like I'd be happy to chat with you about designing a study or what you're really after. But I think there's, yeah, I support interaction effects. I support lots of, I think maybe the best answer to that question is that you should ask your advisor for a bigger computer.
Marty.
So just along those lines, I mean, you have a really nice but with open you've got the set steps where you've got the joint moments and the inverse kinematics and things like that. So you were having to take outputs of one model, like distributions of outputs of the model, and form new, I guess, distributions of those outputs that you can select from for the next step. Is that a easy process to do, or for the output? How do you form those distributions of the outputs?
I don't think it's that bad, right? You essentially capture that data, and it could even, so I think you would, as you perturb your inputs, you would just carry them forward,
so
right?
At each step there was a relatively small number of outputs, I guess, that you need to form distributions from.
Yes, yep, and then it just carries forward into the next piece. And I think most of what's developed in that probabilistic plugin will I think manage that. Yep. Yep.
Go ahead. Here's another question along those lines. So, when you're adjusting the cup size and orientation or position, are you then going back to, in your open sim loop, to recalculate all of the muscle forces, kinetics through that whole pipeline? Or are you just saying, well, okay, now that the geometry's changed, that's going to influence, pardon me, maybe just the moment arms and muscle tendon lengths and putting that back in? Would you go right to the very top and run it through the whole sequence?
So I think we build that model and run it the whole way through.
Okay, so it's running through each entire sequence. So
Yeah.
when you adjust your anatomical variation, then everything else that is associated with that then falls through.
Yes.
I've seen it before where people kind of do interim steps in between, but it
Okay.
seems a bit unsatisfying because you might think, well, of course, the anatomy is going to influence the moment arms and muscle tendon lengths, and that would influence, obviously, the forces and the moment capacity of the muscles. So,
Yeah.
thanks.
Yeah, actually, that was my question.
Oh.
That assumption of independence of
Yeah.
those distributions, but if you're going all the way through, it's much better.
Yep.
Oh, if there's no more questions, I'd like to thank you again for stopping by New Zealand on your way home. And come again, come spend a bit more time next time.
Okay, deal.